Welcome back to the video. In this video, we'll be understanding Malus's law. So, for us to understand this, I'm going to explain the setup real quick. So here we have got a plane polarized light, which is vertically polarized, and we're looking at an electric field here, E. So E will represent the electric field. So we're looking at the electric field. Now, you probably would want to know where this connection comes from. So we're looking at light, and we know light, there's another name when we talk about light. It's called electromagnetic waves, right? They're made of electric field and magnetic field. The reason in optics, when we look at light, we specifically focus on the electric field because the interaction between electric field is much dominant in optics than it is with the magnetic field. Okay, so we're looking at an electric field here, okay, and it is vertically plane polarized. So when the electric field is there and we have placed a polarizer, now here we have a polarizer, and this is the axis of the polarizer, the axis of transmission of the polarizer. Okay, so I hope that is clear. This is the axis of transmission. Okay, now what's going to happen here is that, give me 1 second, let's erase all of this now. So let's say that now this vertically plane polarized light will come here and will reach over here and will pass through the polarizer. Okay, and now when it passes through the polarizer, it will form an angle theta with the polarizer, with the transmission axis of the polarizer. And that angle theta is very important because when that angle theta is going to form, here it's phi, but I'll just say theta, we can see that we can make the electric field into two components. We can say this is going to be E cos theta and this is going to be E sin theta. Let me try to make it in the diagram above. This is going to be E cos theta. Let's say this is E naught. E naught cos theta, and this is going to be E naught sin theta. Okay, it's similar to how we do it, the resolution method. We have a resultant here, and then we make it into two components. That's the same thing. This is going to be, let's say x cos theta, and then x sin theta. So that's the same thing we're doing here. Now, if you notice here, this component E cos theta is parallel to the transmission axis. Okay, and then E naught sin theta is going to be perpendicular. I think it's better visible with this diagram. So you can notice there's a 90-degree angle. So E sin theta will be absorbed. It's gone. It has been absorbed. E cos theta will pass through. So then we have the wave, the light wave that we have. It's going to be having the electric field strength then as E naught cos theta. So I hope that's clear. So initially it was E naught, and then now it's E naught cos theta. So I hope that's clear. So the electric field strength, I'm emphasizing that word, we're looking at the electric field strength. The electric field strength, electric field strength. Okay, so the electric field strength E, which is going to represent the electric field of this, is going to be equals to E naught. E naught was the initial electric field strength, cos theta. Okay, so this is our equation. Now there's two relations you need to know. One is intensity is proportional to amplitude square. That amplitude is directly proportional to electric field strength. So using this, what we can say is that the intensity is proportional to electric field strength square. And then what we can do is we can say E square is equals to E naught square cos square theta. And then we can say this was the intensity, not square, intensity is equals to I naught cos square theta. Okay, so that's what we're going to be looking at. So this is the intensity after the light has passed through the polarizer, and this was the intensity initially that the light had before passing through the polarizer, and then have the cos square theta. Okay, so I hope that's clear. Okay, now let's try to do a question on this. This is going to be November 2023, paper 2-2. So question 5, it says a beam of vertically polarized light. So vertically polarized light is incident normally on a polarizing filter as shown in figure 5.1. The transmission axis of the filter is initially vertical. The filter is then rotated through an angle of 360 degrees while the plane of the filter remains perpendicular to the beam. And then it says in figure 5.2, sketch a graph to show the variation of the intensity of light in the transmitted beam with the angle through which the transmission axis is rotated. So there are a couple of ways to do this. 2 ways actually. The first one is understanding it theoretically. So I have a diagram here, the same thing. And we can notice here that initially they both are parallel. The vertically polarized light and we have the transmission axis also vertical. So we have the maximum intensity. Okay, this is I, max I. So its intensity remains the same, maximum basically. And then as you're going to rotate it and the vertically polarized light and the transmission axis are now perpendicular to each other, now the intensity is going to be equal to 0. None of the vertically plane polarized light will pass through. So going from 0 to 90 is going to make the intensity of the light to go to 0. And then similarly, if you go from 90 to 180, it's supposed to go up. So something like this. And then again, down. So every 90, this pattern will be seen. So 90, it goes down. And then from 90 to 180, it's going to go up. And then every 90, you can see there's that pattern. And if you actually want to do it the second way, which is just memorizing the graph, because this comes up a lot, is we can use Malus's law here. Cos square theta. You can see the function cos square theta. This is just the graph of that. That's pretty much all it is. It's just a graph of cos square theta. And that's why it has a pattern. It's periodic. Okay. So I hope that's clear. The next part is actually really, really easy. Just use the equation I is equals to I naught cos square theta. Here, our intensity of the incident beam, this is going to be 7.6. The transmitted beam intensity, 4.2. And we're supposed to find theta. So let's just solve that. So once you solve that, you should get an answer of 42 degrees. Okay, so I hope that's clear. And yeah, that was the answer. Let me just show you the mark scheme as well. Here is the mark scheme. And yeah,